It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farmers Really Nice Coffee.
Hi guys, welcome to the 9th video for the organic chemistry topic. This one is on triglycerides. Now triglycerides are basically esters, okay, and triglycerides are what we use for talking about fats and oils, hence the sumo wrestling. So a triglyceride is an ester of glycerol, which is this molecule here called propan-1,2,3-triol. Right, it's an alcohol, and what we call a fatty carboxylic acid. So a carboxylic acid that has between generally 12 to 20 carbon atoms. That's the ones that make up a triglyceride. Now, as you would expect, because it's an ester, okay, we have only this polar carbonyl group here, and the rest of the molecule and this long carbon chain is non-polar. So they're very organic molecules, and what I mean by that is they're very non-polar, so they don't dissolve in water. They generally have held together by secondary dispersion bonds between the carbon chains. We're going to look at how that differs between what we call fats and oils. So a fat is where the carbon chains have no double or triple bonds in them, and so what we call it is the term saturated. It has the most amount of most amount of hydrogen possible within the molecule. So you can see over here we've got the chains, the long chains, and if you don't know about how drawing these and using these in chemistry, basically each of these points here is a carbon atom through here. Okay, so this is actually a CH2 all the way through, and you need to know this when you're working out how many carbons are in the chain. So this one right down the end is a carbon. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there, and then there's the 11th carbon on there. So it's probably right on the bottom end of what we call a fatty acid. And you can see that when we get 3 of these and we link these up to the glycerol, we get 3 ester condensation reactions occurring here to form 3 separate ester groups, 1, 2, 3, like that, with 3 long chains. Now these long chains, you can see they stack along really nicely, and I call this the Pringle effect basically. What that means is that you've got one chain here, and you have to excuse me, my voice isn't so great at the moment, so I'm having a bit of trouble speaking. Right? You've got one chain here, you've got another chain that stacks really nicely on top, so you get lots of secondary dispersion bonds that occur between these chains, and then you've got another chain that stacks on top of that as well. So you get these layers of chains that all stack really nicely together. You get lots of secondary dispersion bonds occurring between these chains, so they're held together reasonably strongly. Now what that means is that they have a generally higher melting point, which is why they're a solid at room temperature. So they're fats. Okay. Now fats we generally tend to get from land animals, so a really good example thing here, but this is things like pigs. Pigs have a lot of fat in them, alright. Other land animals, we have fat in ourselves, some more than others as well, depending on how much iced coffee you drink, and so that land animals is our main source of that. Now that differs from oils in one very distinct way. Now oils have double or triple bonds in their chain, and it may not seem like a big difference when we've got a double or a triple carbon bond within the chain compared to no double carbon or triple bonds within the chain as we had in the fats, but it has actually quite an impact upon the way that the chains stack together. So hopefully you can see this. So this is an example of just a long chain which has no double or triple bonds in it. So you can see we've got the tetrahedral arrangement around each carbon atom, and you can see we've got this sort of nice sort of straight chain form. I'm going to show you what happens when we introduce a double bond into the chain here. So I'm going to break this one here, okay, and what I'm going to do is we obviously lose some hydrogen out of the chain, and so I'm going to put in a double bond, and I want you to see what effect that has upon the structure where we have those nice tetrahedral arrangements around it. Okay, what I want you to now have a look at is, hopefully you can see that now. Here's the double bond that I've put in, you can see it there between the 2 carbons, and instead of having this nice straight chain that we had, you can see that we now introduce what's called a trigonal planar arrangement around each carbon instead of a tetrahedral. And what it does is it makes the chain go across and then start to come down. Now you can imagine if you add another double bond in here, you actually start to get a chain that isn't straight anymore. Okay. Now what that means is that when these all stack on top of each other, instead of being the Pringle effect like we have with the fats where we get lots of secondary dispersion bonds between it, you start to get now a chain which now has a kink in it like this. So when you get another chain on top of it, right, you can see that there's not as much bonding that occurs between them. So we have less secondary interactions between the chains, less dispersion bonds. Over here, you can see that. So we've got some bonding here. But over here, this gap is too big to have any secondary bonding. So we've got some secondary bonds here, right, but we don't have any through here. Less secondary bonds means we have a lower boiling point and melting point because there's less energy required to actually break the molecules apart from each other. And that's why oils are liquids at room temperature, because of this double or triple bonds which change the shape of the actual chains and how they stack with each other. Now sources, as I've talked about, fats normally come from land animals. All right? Oils we generally get from marine animals or plants. So you need to think about the sort of oils you normally have around your house. So canola oil, sunflower oil, and then things you take for your health. You take fish oil, for example. So you know that they come from marine animals or plants. Whales in particular were hunted a lot for their oil. It burnt really well. They used to use the whale oil in lighthouses. Okay, whereas fats come from land animals. Okay, so have a look here at these triglycerides that we've got. Okay, so we've got these are actually fatty acids that we've got. If we use these to make a triglyceride, hopefully you'll be able to work out which one would make a fat and which one would make an oil. Okay. Now, if you just remember what we've just gone through, if it's got a double or a triple bond in there, it's unsaturated. The chains will kink. There won't be as much secondary interaction, so it will form an oil. So this one, oleic acid, has a double bond. That's unsaturated. Linoleic and alpha linoleic. All right. All three of these will make oils because you've got double bonds in there. Palmitic acid and stearic acid, both of these will make fats because there's no double bonds there, so the chains stack really nicely on top of each other. Now we can tell how many double bonds we've got in there through something called a degree of unsaturation test. So when we've got those double or triple bonds in there, a double or triple bond is actually a functional group. So an alkene and an alkyne are a functional group in a molecule, and we can add things across that double bond. The most common thing we do is add bromine water. Now bromine's an orange colour, so you can see over here we've got some bromine water. Okay, and then what we do is if we shake it with an unsaturated triglyceride, all right, so in this case an oil, all right, so you can see it's got this sort of oily droplets through there, but what we've done is we've actually created a colourless solution. So we go from orange to colourless because the bromine is added across the double bonds. Okay, if you look closely, you can actually see two layers here. We've actually got an organic layer and an aqueous layer, and all the bromine has come out of the aqueous layer, which is bromine water, and it's gone into the organic layer, added across the double bonds, and we've got a colourless solution now because there's no bromine in there. You can also use iodine, which is more of a purple colour, but iodine's a solid at room temperature. It's much easier to use bromine, which is naturally a liquid, to dissolve it in water and use that. Now I've got here every mole of double bonds requires 1 mole of bromine or iodine in there, so that's not just like one double bond requires a mole of bromine. You got to think about it in terms of a mole of the molecule. In a double bond will require 1 mole of bromine in there. So you can easily work out basically the degree of unsaturation by how many moles of bromine you add via titration. And I've got in here a triple bond is equal to 2 double bonds, and what I mean by that I'll show you on the next slide. Okay, but what we've got here is we've got an oil, right, because we've got double bonds, and we're adding in some bromine to it. You see we've got 1, 2, 3, 4 double bonds in there, so we add in 4 bromines, okay, and you can see the bromine adds across each of the double bonds here, and we've turned it from a liquid up here with double bonds to in here. Probably this is going to more be a solid because we've got no double bonds there, and these chains will start to link together a bit more nicely. Now when I'm saying that a triple bond is worth 2 double bonds, if you've got a triple bond like this, right, between the carbons, and you add in some bromine water, all right, you're going to end up with breaking one of the bonds to end up with this. All right, so you add your bromine in across double bond, okay? But because you've got a double bond, you can then add more bromine in, okay? And then you can end up with something like this, where you'd have more bromines on there as well, okay? So you can see a triple bond here actually adds bromine twice, so it's the same as 2 double bonds, okay? So that's where you've got to be careful around, just assuming that because you had a certain number of moles added, that you can identify it as a just double bonds. But generally, when we're talking about fats and oils, we only have double bonds in there, and so that's the main thing that needs to happen. What they're going to ask you about this in the exam is probably pretty much around the colour change, or how you can distinguish between a saturated and unsaturated triglyceride. So you add bromine into it, and the bromine will get decolorized, so it'll go from orange to colourless in the presence of a oil which has double bonds in there. Now, because they're esters, you can hydrolyze them exactly as you did in the ester topic we looked at before. So you break the carbon-oxygen bond here to get your propan 1,2,3 triol or your glycerol back out. Okay, and then you actually get your 3 individual fatty acids. So here we've got 2 which are straight chain, and we've got 1 here which is a double bond in it as well. So this would have been an oil because it's got a double bond in there. Okay, and we're just hydrolyzing it back to get the carboxylic acids and the alcohol. Alright, and again, because we are doing it as an hydrolysis of an ester, we can do it under alkaline conditions as well to get the deprotonated acid, which is this one here. Alright, we get the carboxylate ion and we get our glycerol back. Now this is really good because we use this in soap formation. So if the one we use is actually sodium hydroxide here, Na+, what we form at the end here is the sodium carboxylate salt for each of these. Okay. Now, the sodium here on the end allows us to form ion dipole interactions with water, which actually makes all of these soluble. Even though we've got these big long carbon chains on them, because we've got the ion dipole interaction of the sodium here on the end, all right, we can make them water soluble. And so this is actually how soaps work. So we went through soaps a little bit earlier in one of the earlier topics, but basically a soap has a long hydrophobic or water-hating tail. This is non-polar. Okay, this is what bonds to other oils and fats. Okay, so we use that to bond to oils and fats. And then we've got our polar head group over here, which is hydrophilic. That does ion dipole interactions to water. And we get these micelles being formed. So there is a video on cleaning agents and how they work, all right, through the 4 steps, which is penetration, where the hydrophobic tail here attaches to the oil and the fat particles or the lipids in your solution you're trying to clean. You've then got your agitation, where you break them away from the surface. Then you've got your micelle formation, which is where we form the oil or lipids in the middle here, because they're non-polar. They don't want to be with the other water molecules, so they clump together like this, with the polar head groups on the outside, which repel each other, which is the final step, and that's deflocculation, which allows us to wash them away. So that's been covered in the previous topic, and there is a separate video on that as well. So I suggest you have a look at cleaning agents and how they work. And so we've used it a fair bit before, so I'm not going to go into too much more depth now. If you want to convert an oil into a fat, you can actually do that. As we did the degree of unsaturation, where we added bromine across the double bonds, we can actually add hydrogen across the double bonds, and this is called hydrogenation. So up here, if we've got canola oil, which is what this is, right? This is one version of canola oil. Canola oil has a lot of different fatty acids in it. If we add some hydrogen across it with a nickel catalyst, okay, you notice we add across some of the double bonds, and now we've turned it into margarine. Now, the reason we don't add across all the double bonds is, remember, this is a liquid because those chains don't stack nicely on top of each other. Okay, we add across some of the double bonds to increase the number of dispersion bonds, to increase the melting point, so we turn it into a solid. We don't add all of them across though, because if we added across all of the double bonds, we'd get a very high melting point solid, and it'd be really, really hard to spread this. You want this as a solid which is soft at room temperature, which allows you to spread it over your bread. Okay, otherwise you get really, really hard materials, which makes it really hard to spread. And so that's why you don't add across all the double bonds. In terms of practically how they do the hydrogenation, they take the oil here, they add in hydrogen gas, and they form it into a fat. Now, because oils are liquid and fats are solid, the the only gaseous molecule you've got is hydrogen in there, and so this reaction is quite susceptible to pressure, because the only thing you can compress with pressure is a gas. If you increase the pressure, you force the equilibrium towards the product side, because it wants to get rid of the gaseous molecules that are in there. So the equilibrium shifts to the right and favours your formation of the fat, so you get a higher yield. Okay. We also use high temperature to increase the rate of a reaction, and we use that nickel catalyst, as you saw, to also increase the rate. So this is an actual general hydrogenation process container. So you've got your oil in here, you add your hydrogen gas in under pressure. Alright, you stir it around to mix the oil and the hydrogen gas. Hydrogen adds across the double bonds. Alright, you get your fat in there, and once it converts into your fat, you can then just separate it out from the liquid. So what they'll ask you in terms of this is just to, I guess, maybe talk about how you convert an oil into a fat and some of the conditions necessary. And again, it just comes back to collision theory and rate of reaction, which is what we've looked at before. Alright, that's been this topic on triglycerides, a little bit longer. Hopefully it's made a bit of sense. The main things you need to be able to do is obviously be able to draw the structure of a triglyceride given the fatty acid that you're using. You need to be able to do the hydrolysis. You need to be able to tell the difference between a oil and a fat. Alright, and you might also be able to need to go through and talk about how you convert an oil into a fat as well. Alright, hope this has made sense. And always, if you've got any questions, just ask. Thanks, guys.
This is your love.